This is part 10 of the series Circles, and in this part we're going to look at a new theorem. It's called the circumscribed angles theorem. A circumscribed angle is an angle whose sides are tangent to the circle. So over here you can see that angle A has sides AC and AR, and they're tangent to the circle at point C and point R. The theorem states that the measure of a circumscribed angle is equal to 180 minus the measure of the central angle that intercepts the arc. So the measure of this angle is equal to 180 minus the angle CTR, that intercepts that arc CR. Now this may appear to be similar to the angles outside a circle theorem, specifically in the case where you have two tangents. And it would be fairly close to it. The angles outside a circle theorem states that this angle is equal to this big angle, this big arc, minus the small arc divided by 2. There may be circumstances where it's more convenient to define this angle in terms of the central angle that intercepts that arc. So that's why we have this theorem. Consider it a shortcut to one of the other theorems that we've learned. Alright, let's take a look at where this comes from, because it may not be intuitively obvious where this theorem comes from, and in fact the proof is a little bit complex. So let's strap in and take a look at this proof. Here's the setup of our proof. We have a circle, we have two rays DC and DA that are tangent to points C and A, tangents at points C and A, and so that makes angle D, or ADC, a circumscribed angle. And this angle we have to prove is equal to 180 minus the measure of angle APC. So this angle should be equal to 180 minus this angle here. So let's go ahead and put in our givens, write in our auxiliary lines, and talk about our plan for the proof. So here what we've done is drawing in ray DB, and we've created these angles, angle 1, angle 2, angle 3, and angle 4. And the plan for the proof is going to be to show that this triangle DAP and DCP are congruent, and then using the fact that angle 1 equals 1/2 the measure of this arc minus this arc, we can show that because these two angles are congruent and these two angles are congruent, there's a relationship between this circumscribed angle here and this central angle. So let's dig in and start this proof, and we're going to start with showing that these two triangles are congruent. And to do that, my first statement is going to be that radius PC and radius PA are congruent. So let's write in that statement. So here we have PC is congruent to PA, all radii are congruent. We also know that segment CD is congruent to segment AD because of the exterior tangent segments theorem, and so we're going to write that next. So here we have CD is congruent to AD, and external tangent segments theorem says that if two external tangent segments meet at a common external point, those segments are congruent. And we also know that PD is congruent to itself by the reflexive property. So PD is congruent to PD by the reflexive property of segment congruence, and the whole purpose for doing this was to show that triangle DCP is congruent to triangle DAP by side-side-side congruence. Now, I know that angle 1 and angle 2 are congruent, angle 3 and angle 4 are congruent by the CP-CTC definition. Corresponding parts of congruent triangles are congruent, and therefore the measure of angle 1 is equal to the measure of angle 2, and the measure of angle 3 is equal to the measure of angle 4. So I'm going to take some liberties with the proof and combine those steps into one statement here. So again, angle 1 is congruent to angle 2, 3 to 4, and the measure of angle 1 is equal to the measure of angle 2 by the definition of congruent angles, and the measure of 3 is congruent to the measure of 4. Now, this work has been mostly preliminary. Now I need to start establishing the linkage between this angle, angle ADC, and angle APC. So let's first start with the fact that the measure of angle ADC equals the measure of angle 1 plus the measure of angle 2, and the measure of APC is the measure of angle 3 plus the measure of angle 4. And we're going to use the fact that angle 1 is congruent to 2 and angle 3 is congruent to angle 4 to combine those into one statement. So let's go ahead and show those angle sums. Here we've stated that the measure of angle ADC is equal to the measure of angle 1 plus the measure of angle 2. So 1 plus 2 is ADC. The measure of angle APC is the measure of angle 3 plus 4. So APC is angle 3 plus angle 4, and that's the angle addition postulate. Now, given the fact that angle 1 is congruent to 2 and the measure of angle 1 is equal to the measure of angle 2, we know that the measure of ADC equals 2 times the measure of angle 1, because angle 1 plus angle 1 is 2 times the measure of angle 1, and the measure of APC is angle 3 plus the measure of angle 3, which is 2 times the measure of angle 3. So that's the substitution property of equality coupled with simplification. So rather than write two separate statements, I just combine them into one here. So hopefully you can see that we would have written the measure of angle 1 plus the measure of angle 1, and then a second statement to simplify. The measure of angle 1 plus the measure of angle 1 is 2 times the measure of angle 1. Now that we've established the identities of angle ADC and angle APC, it's time to tie them together with this angle outside a circle theorem idea. So that's the next step, is to show that measure of angle 1 equals 1/2 this minus this. So here we have the measure of angle 1 equals 1/2 the measure of arc AB, which is the big arc here, minus the measure of arc AE, which is the small arc here. And that's angle outside a circle theorem. Now I've pretty much run out of space here, so what I'm going to do is I'm going to copy down the proof statement down here, and I'm going to scroll up a bit so that we have some more space that we can work with. This is obviously quite a long proof, so let's go ahead and move that. Now in the statement we're trying to prove, we need the measure of ADC out here on one side of the equal sign. And you can see that up here we've established that ADC is 2 times the measure of angle 1. Well, if I take this statement and multiply both sides by 2, I'll have that idea. So I'll have 2 times the measure of angle 1 on this side, and then I can substitute my measure of angle ADC in for that. So the first thing, we're going to multiply by 2, and then we're going to substitute the measure of angle ADC for angle 1. Here we've said that we multiply both sides by 2, so 2 times the measure of angle 1 equals the measure of arc AB minus the measure of arc AE, and that's multiplication property of equality. Then I substituted 2 times the measure of angle 1 here with the measure of angle ADC here. So the measure of angle ADC is now equal to the measure of AB, arc AB minus the arc AE. Now here on this final proof statement, we have to have a 180-degree measure. So the way we're going to get that is we're going to establish, because we have arc BAE is a semicircle, because BE is a diameter, we know that the measure of arc AB plus the measure of arc AE is 180 by the arc addition postulate. So that's going to be our next statement. So here we have our first statement, the measure of AB plus the measure of AE. So AB plus AE equals 180 degrees. So that those two angles equal a semicircle. That's the arc addition postulate. Then I just subtracted the measure of arc AE from both sides. So the measure of arc AB equals 180 minus the measure of arc AE. And that's the subtraction property of equality. Now I have an expression for the measure of AB in terms of 180 degrees. So I can take that expression and substitute it back into here. And so that's what I'm going to do next. We're going to substitute this expression for AB in here. Now we're getting closer. We have measure of ADC. Measure of ADC equals 180 minus the measure of AE minus the measure of AE. Well, clearly that is the measure 180 minus 2 times the measure of AE. So that's going to be our next statement. Here we've just consolidated. The measure of AE minus the measure of AE equals 2 times the measure of AE. Now we need to get some more space, so we're going to scroll down a little bit more. We're closing in on the proof. We have 2 times the measure of AE, so 2 times the measure of AE. And we can clearly see that because this angle and this angle are congruent, this arc and this arc are congruent. And so we need to get this in terms of the measure of angle APC. Now the way I'm going to do that is I'm going to establish the fact that the measure of angle 3 equals the measure of arc AE, which is the definition of the measure of a minor arc. And then we should have something that'll tell us that this angle times 2 is going to equal APC. So my first statement is to relate angle 3 to arc AE. Now we've stated that the measure of angle 3 equals the measure of arc AE, so we can do a substitution at this point and say that this expression is 180 minus 2 times the measure of angle 3 because they're the same. So that's going to be our next statement. With this statement we're almost done. We have the measure of angle ADC. The measure of ADC equals 180 minus 2 times the measure of angle 3. And we have to get that to be equal to the measure of angle APC. So let's look back, and there was a statement, here it is right here. The measure of angle APC equals 2 times the measure of angle 3. So now we can do another substitution and replace our 2 times the measure of angle 3 here with the measure of APC, and we'll have our proof completed. So that's our final statement. And there's our final statement. The measure of angle ADC equals 180 minus the measure of APC. And now I will grant you that this was a pretty aggressive proof, and this is by no means the only solution. You will probably be able to come up with something more elegant, more streamlined, but it's the entire thought exercise that increases the geometry student's abilities. It's not necessarily the completion of a proof like this, it's the ability to think through it. As you think through and have a knowledge of these theorems, definitions, and postulates, and the idea of synthesizing them and putting them together in a logical sequence is the thing that locks this information from short-term into long-term memory so that you can apply them much better in practice, and it makes the entire course of geometry much easier. So with that, let's go ahead and take a look at an example. In this example we're given the circumscribed angle is x and a central angle of 127. We know that the formula is x equals 180 minus the central angle of 127, which is 53 degrees. So much more streamlined than using the angles outside a circle theorem. Let's look at one more problem. In this example we have the circumscribed angle and we're given an inscribed angle. The measure of the inscribed angle is half of its intercepted arc, so this arc is 2x, and that arc is the same as the measure of the central angle. So our formula becomes 35 equals 180 minus 2x, taking the place of the central angle, add 2x, subtract 35, and divide by 2. So x equals 72.5. I hope that was a little bit helpful, and I'll talk to you in the next video.